Right, hey everyone, let's get this thing going. Welcome back to another week of Hobby Kernel Dev Gardening, week 21. And we're doing virtual memory again. Let me just do another test in the chat to see if the chat widget is working, because it seems to be very finicky week to week. It would be pretty nice if that worked, but whatever. Hey, Cat Flare. Hope you're doing well. Hope you're having a nice day. Chat works. Yeah, I'm kind of expecting to see like the chat texts pop up in this white box I have at the top. But sometimes it just doesn't work for reasons I don't understand. Which is too bad, but whatever. Yeah, it was working pretty well at some point, and then it just kind of stopped. Yeah, anyway. I kind of just want to get back into it, and maybe that thing can figure itself out later. Yeah, kernel virtual address space, that's what we're working on today. And I want to give a shout out to Dhruv, who pointed out a bug in what I was doing last week, which I'm going to take a look at now. So last time we are working on this like exercise where it's time to set up the kernel virtual memory, and we have a few things we need to do. We need to map the pages region read only at the user by the user at linear address U pages. And I had started to kind of I'd started to do this a little bit manually. Test 4. Man, yeah, what's going on? Come on, Streamlabs. Like, so far nothing is popping up, which is kind of unfortunate. I'll just try to... I never really know how to troubleshoot this stuff. I click save settings. I don't know. Yeah, it's a public stream. Oh, okay, we got the test. We got the test 4. So maybe there's just some delay. Maybe it just, or maybe I don't know. It's like I see the test 4 now. That's the first one that I've seen, but I don't see that in my OBS window for some reason. So whatever. It's not that important. What's more important is this code. So I was doing this a bit manually. Also, I don't quite know how to pronounce your name, but Joao. Cool. Yeah, thanks for joining. Right, I was doing this a bit manually. So the goal, and I was also still kind of struggling to understand these instructions. It says map pages read only, use the linear address U pages. And for just a bit of context to get like warmed up again, I finished part 2 of this thing like in the last couple weeks, and now I'm moving on to part 3. And the goal is to implement the virtual memory layout, which is described here. This is the kernel's virtual memory layout. We're still in the process of like booting up the system, and I like 2 hours a week is not a lot of time to make quick progress on this, and so we're still kind of in the boot process, and we're still just kind of in the early stages of getting the kernel going, because up until this point, we've been using a really basic virtual memory system, and it's missing a lot of things, which I kind of still don't fully understand, but because I'm just kind of going through this as I go, but it's missing a lot of things. So now we're implementing the production virtual memory test 5. Sick. I'm gonna chime in there with the test 6 just for fun. Yeah. That's fine. Okay. Okay, finally seems to be working. It's like a little bit slow, it seems, to get the chat going, but yeah. And so, yeah, so specifically, the part of, like the first baby step of the kernel virtual memory thing that we're setting up is this pages thing. So pages is the set of data structures behind the physical memory allocator that we have. And frankly, I don't actually know why it's asking us to do this. It's kind of a odd thing. It's like a kernel data structure, and it's telling us we need to expose it in a way that's readable by user space, which I fully don't understand why we would need to do that, because it's like a kernel data structure. But that's what it's saying. And last time I was doing this kind of manually, and Dhruv pointed out that I had actually already implemented a function that was maybe like already doing kind of what I want here. And I totally forgot about it. It was this function called boot map region, which was kind of from an earlier exercise. And I guess we've actually never used it. Yeah. The only references to this so far are basically in the definition and the implementation of the function, and there's no callers. And so Dhruv pointed out that maybe I should consider using this. And that's where we are. And so let's get going. I still like need to kind of understand and remember what's happening here. Maybe it'll help to read, a bit of what's going here, but it's not mentioned in this documentation, so that's actually not that useful to read. But yeah. So just to recap, what was I trying to do? Like forgetting for a moment that I had this function called boot map region. What was I trying to do? So we have the pages thing, and in my code I've renamed it to G pages to make it more clear that it's a global variable. But there's a certain section of memory which is all like basically an array of struct page info structures. And it's telling us that we need to map this read only by the user at this specific address in virtual memory. With these certain permissions. And here's the part I wasn't totally getting. Like it's saying, I don't like the new image at pages itself. So this is kind of the part I was starting with. We're just mapping this pages thing at the pages address with very specific, with like read only permissions for some reason. And then it's also saying map pages itself, which I actually don't really know what that means. Because I kind of thought this one was also like it's just one set of data, but I guess we are going to have two mappings of this data. But to be honest, I don't actually understand. I just do not get that. And in order to move forward with this, I am going to need to read these checker functions that come later and see what they actually are testing for, which is one of the nice things about doing this in the context of like this coursework, is that I'm like not really a pro here, and so it's useful to have some built-in test functions that are provided for me to know if my code is right. So yeah, it says your code should now pass check kernel pagedir. Just quick check, just wondering how the music volume is. I can't actually hear it because I can't, I don't want to listen. Like I can't really concentrate very well when I'm listening to music, but I like the vibe of that it gives to the streams. So I have my computer muted right now, but I hope the volume is okay. Okay, but it's saying coach now check should pass check page dir, and that's what I'll use to understand what I actually need to do later. But for the moment, I do understand the basic principle about this first one. We're mapping you pages at a certain address. And in order to do that manually, here's what I was doing. I was computing the size of this page's array, basically. It's an array of struct page infos. And we have some, we have already computed a few things from before. So we know the number of pages that exist. It's the number of these physical memory frames or physical memory pages. And we also know the size of the page info structure, so we can compute the size of this array in memory. And then the idea, like the loose idea, hey, digitalized, it's going pretty well, but yeah, just kind of working through this next part with setting up kernel virtual memory. And yeah, this stream will be interesting because I kind of don't know what I'm doing. But yeah, like always, we're just going to figure it out together. So what I was doing is I'm trying to map this region into memory, and the basic idea, I think, is that for each page, we need to actually add a page table entry for each page. So I feel like I should visualize this to help myself understand it. All these like random blocks and stuff. Let's just let's just go over here. So there's this big array in memory. It's the pages. It's G pages. And the goal, yeah, it's like a collection. I think I kind of visualized it over here. It's basically this long array of these structures, and G pages points at the front. And the idea is to map this into memory at a specific virtual address. So if we go over to our virtual memory diagram, boot out, I think it's even in the boot alloc region. So currently, so in physical memory, like, let me just, I like, it's not strictly necessary to reference this, but I kind of just want to see, let's see, and I want to go to boot alloc, or where does G pages set? Here is the specific place. So we're initializing memory and or whatever, and we do the same thing I was just showing. We compute this full size. We query, at some point we like queried or looked up how much memory is physically available in the system, which allowed us to compute the size of the array. And then we requested that much from the boot allocator. And the boot allocator is this dumb thing where it's like the simplest possible ever memory allocator, where it just takes as a pointer, it finds the end of the kernel and just starts bumping along after that. And it allocates this array immediately after the kernel. And so in physical memory, it's going to be right after the kernel, which is in this kind of low memory region. But in our really basic virtual memory setup, we've basically just mapped this region to point there, and the kernel is operating with these addresses. So at the present moment, the G pages array is kind of like approximately around here in virtual memory. what we're trying to do is then, and I don't exactly know where it is, but at some other point in virtual memory, it's called like user pages, I think, or what was the name? U pages, right? Yeah, U pages. And so at U pages, I have no idea where this is actually right. It's somewhere else in virtual memory. We are going to, I guess I'll need to just make another rectangle. We're making another mapping that is going to actually point to, this arrow is like kind of weird, but it's going to actually point basically right there. And I kind of wanted it to be straight. Okay, this is getting a little bit messy, but something approximately like this. We're adding another entry to the virtual memory mappings that is going to point here. And so that means that data is actually kind of mapped twice. It exists up here because we have the first, I guess, 4 megabytes mapped right here in this region. Then we're going to have another mapping that kind of points at a pretty similar place. That is the immediate goal as far as I understand it right now. Just check in. Okay. So, that's the code. Right, and what I was trying to do, and so basically the idea was like, okay, I here, so I is actually like an offset into this page's size variable that's computed, like the size variable. And the idea was for, you know, the idea is that it bumps along in page size chunks along this thing. And so remember I mentioned we have this, I'll drag it a little bit closer. We have this G pages array, and it's pretty long. It's like, it's very like, I mean, specifically we have 128 megabytes of memory. And so it's 128 megabytes divided by 4K or whatever, which is, I mean, I think we computed this all last time. Yeah, it's 32, it's over 32K pages. It's like a lot of memory. Right, because each of those is a page. And so this array, yeah, that's num n pages, and then this is the full size of this thing. So it's like 262 approximately kilobytes of memory. So this is like this is a really long array. 260K of data. And we're kind of going along and slicing it up into these like 4K, you know, pretend that those are equal. Like, I don't really know how to pretend it's like equal. We're slicing this up into 4K chunks, and we have like some kind of pointer that's going to just advance. It's going to start out kind of here, and we're just going to here we're going to map each page as we go. So we start here, but then bump it to the next 4K, and bump it to the next 4K, next 4K, and so forth. And that's what I was trying to do with this code. So I is basically that like pointer thing I was just showing, and it bumps along every page size, which is 4K. And we start out just at G pages plus the offset. And we kind of do this like kind of like a little bit of like a dance to go from this virtual address, kernel virtual address, convert it into a page info, which is what we need for page insert. And then we can call this page insert function we've been writing over the last few weeks, which does all of the dirty work of mapping a page. And what all you do is you pass in the page directory you're trying to modify. For us, we just have one basically. It's like this global thing even. I kind of also didn't understand that. But yeah, we have our page directory. We have the page info representing the physical frame we're trying to kind of like point at with our mapping. We have the virtual address that we're mapping the physical frame at, and then we have the permissions. And that was kind of it. That was like where I left it last time. But then Drew mentioned that we have boot map region. Let me pull up the comment actually, because it was a really good comment. It's very sharp. I'll go to, can I just like browse to my own YouTube channel? Last time, so that was week, pause. And Drew left a comment. How do I see the comments? Here we go. Drew mentioned, we can use boot map alloc region rather than running the loop. It says static mapping, blah, 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 blah. So yeah, so that just for reference and credit to Drew. So let's take a look at that. Boot map region, right? So, and I mean, this thing does kind of something similar, but it uses pagedir walk instead. What does it do? Map a specific range of virtual address space to a specific area of physical address space, which actually is pretty much exactly what we want to do. I think it's right. I think what I'm doing is like kind of wrong. I think this is the better way. This function is only intended for the static mappings above utop. What does that mean? So there's all these like mappings we need to implement. And okay, so this is like 0, and this is the top of virtual memory, 4 GB on this system. And user space gets everything at the bottom up until we get a bit higher. And then there's a specific place called utop, which is the top of user space's ability to access virtual memory. I think up above that point, the user space has no permissions to access anything. But below it, it does have access. And there's this interesting region kind of below utop. Normal user stack. U-stacked, that's interesting. Well, I guess we'll get into more of that later, but what does it say? It's like, this is meant for stuff that's above utop, which upages is, like Drew said. So let's try it then. Let's get rid of this and comment it out, and let's figure out how to call boot map region for what I want. And so current page dir is the first argument, and then what? And then you pass a virtual address and a size. So that's going to be upages. And the size is it's actually this thing that so maybe it actually is necessary to compute that page's size. And the last one was what? It was the last two, physical address and the permissions. And so that's actually pretty, oops, whoa, that was interesting. Hit some keys on the keyboard. So actually, so it's gonna kind of be like this line, except this line is not totally right. It's going to be something like this. And I am just wincing at my inconsistency of of like naming style here. Yeah, this is so ugly. Personally, I kind of prefer this camel case kind of thing. A lot of the code in here already is using snake case, and it's just a mess. In the future OS I'm going to make it all consistent and better. But for the moment, I'm just trying to get this to work. But I guess I can call this pages size for the moment. Quick check on the Git. See what our diff looks like right now. Okay. Okay, I think our working tree is clean. Digitalize. Do I read any OS material prior to the stream? Not really. I come in kind of cold to these streams. I don't have a lot of time to do a lot of like learning outside of this dedicated 2 to 3 hour chunk. So not really. I mean, I do just kind of read things that I see, but not in a really rigorous way or really like controlled way or anything like that. Which is PA. And then the permissions was perm, I think. Ah, okay. So I guess a couple of those things inside the loop were useful. Actually, so I'll just move these down. And what is the error here? So a couple errors because I have too many. And I don't even think I need this cast anymore. So let's try to build it. Does it build? It builds. I don't know what I'm expecting to happen if I run it. Well, actually I do. I mean, it's just going to hit the panic. But I just want to quickly double check that this is correct though, because in my earlier draft, are you still building on? Okay, I have no idea how to pronounce your username because it's like 100 underscores. No, actually, I'm not using x86 anymore. I quit x86 in around episode 13, and since then I've been using this thing called JOS, JOS, which if you go to this URL and like explore around the learning materials, that's the course, that's like the OS that we're using for this coursework, and so it's a lot more minimal. It has like x86 is basically very complete already, and this JOS thing like really has almost nothing, which is what I wanted. So I'm not using x86 anymore. Just to recap what this actually does. So take the size given and convert it back into a number of pages. For every page, compute an convert that back into a byte offset and add it to the given virtual address, which produces the virtual address of the page. All right, 20-second break to stand up and stretch. Be right back. Right, so also from base, yeah, so we compute the page virtual address, which, just to bring it back to this diagram, that's kind of like these slash points, and it's also, I mean, this line is very skinny. Imagine this were like a lot longer, and oops, and we had these kind of like, I just want to draw a simple like line going across, but it's like kind of hard to do that. Apparently it like wants to freak out. Imagine we had like all these little lines kind of going across here, like 1, 2, 3, 4. That's what so page VA is. And then we do this page to walk to get the page table entry and also allocate a page table if necessary, which is definitely should not be null for this boot for during the boot process. I'm pretty sure that's why I put the assert there. And then once we have that, we do the final action, which is making it point at the specific physical page address, address we want, which is the physical address plus the offset. It's a very kind of parallel thing. It's very similar to how we compute. We just do an offset from these different base addresses. And then we map that in by overwriting the page table entry pointer, which, yeah, I think that's necessary. It might be possible that we could skip that, but I think in general it's safest to always clear it out. And then just like or in the bits for the the physical address, which is no shifting should be needed there because this is a full physical address, including the 12 bits of zeros at the bottom. So that's a quick recap of how that works, and that basically just sets up. And so that basically sets up the arrow, points from somewhere in virtual memory to where we want to map to in physical memory. So I believe that should actually work, which takes care of the first one, which leads us to now this second one, which I kind of don't get still, pages itself. So, is there something called pages or what? No? Kern base, case, stack top. Current page table, pages. Why changing from dark to light mode, Dixon? I pretty much always use light mode, actually. I think on the very first stream I was using dark mode because I was at night, but usually when I stream it's in the afternoon, like it is right now for me. And so I prefer to have light themes during the day. A lot of people commenting about the color theme lately. That's funny. Yeah, personally, I'm a light theme during the day kind of person, but I use dark themes at night. And that page is there if desired. Okay, I think I didn't find anything interesting or useful there, so which leads me to read this function. So this is the checker function that's ultimately going to check if our code is right. Check that the kernel part of the virtual address space has been set up correctly. It's a sanity check. So what does it do? So it saves off a pointer to the page dir. Check pages array. So okay, end pages is already so that's the global variable that's available, and it computes a size, which it helpfully just calls n, and then for every it bumps along at 4K or page size increments, and does a basic check. So this is really just it. I might actually just start running this code. With a bit of a panic, because I think actually we should already pass this test. It's checking, so it's taking these virtual addresses and resolving them to physical addresses using this check va2pa, and then just making sure that it is equal to the physical address that it should be pointing at. So I think I'm actually ready. Okay. I'm going to, oh shit. Oh, sorry, I got super messed up. A little bit clumsy in my editor today. Okay. Okay. And I'm gonna put this right below here, just in case, but our panic should catch up here first. So, moment of truth. What happens? Panic, it says panic in check current page dir, which means that we got here and we passed all the asserts. Just as an illustration, we could like deliberately inject a bug. Let's say we skipped the first page, actually. So now we are not mapping at U pages, we're mapping starting from, what is the expected expression? Oops. So now with this fake bug I injected, we're not mapping at U pages anymore. We are up mapping from like a little bit higher, like one page higher than U pages, which is not correct. And so hopefully we should see this test fail. And we do it. Assertion failed at, you know, this is 836. Yeah. I kind of want to disable this relative line thing. How do I do that again? Vim disable relative line set. It's like kind of annoying. Set no relative number. Is that right? Okay. There. Now we have like actual line numbers, which is a bit more helpful. So 836. And yeah, that's just to show that we are actually passing the test. And that's just for a bit of commentary from me. Like, I think it's always a good idea to make sure to see your tests fail, and to make sure you are actually writing code that's actually passing them versus something else happening that's causing it to look like it passes, but it's not actually running your code. But the code's working so far. So that shows that this is right. Just out of curiosity, what I want to do is I want to actually go back to the earlier code that I wrote, which should theoretically also pass, I think. Progress, yeah, little bit by little bit. So just out of curiosity, did the code I wrote beforehand that I was doing a bit too manually, does that pass also? I think so. It says panic and check page dir, and I can again inject the bug by starting it at like a weird offset. And assertion failed 864. So actually that goes to show that I did it, that manual work from last time actually does work, but I'm not gonna leave it like that because it's just, we already implemented that function. Yo, Devoid dude, hello from Ireland. Awesome, right on. Nice to have you here. So I'm just gonna go ahead and I guess I'll delete this. I just don't need it anymore. And I'll add this back. Run it one more time to make sure we're going. Panic and check current page dir. Sick. All right, what's next? Always good to know the work wasn't for nothing per se. Yeah. And I mean, even if I did it wrong the first time, or even if I did it the way it shouldn't have been done, it's good to know that I was able, like I was still thinking in the right ways about it, which is just a good sign for that I'm like understanding what is going on. using VS Code, Visual Studio Code. Yeah, I'm a big fan of Visual Studio Code. Okay, so just the next thing is check physmem, which is kind of interesting to me. Okay, let's just use the physical memory that boot stack refers to as the kernel stack. Yeah, I'm using this color scheme called quiet light. Also, I'm like colorblind, so I don't really. Is it pink? I can't see color like very well, so it looks. I can't tell if I'm using like a hot pink, bright pink editor. It looks like it might be to me, but I just choose to have my bar on the right side because when I expand it and it's not so huge, there's not as much movement of the windows. As opposed to if it's on the left side, it moves like there's a lot of window movement. So yeah, I just put it on the right side. Since this thing is like checking physical memory, that's the next check. Check whether white background, light purple. Oh, okay. Yeah, I think I can't like see like. I can't tell the difference between like pink and like purple super well all the time, so it's interesting that it's purple. But white in the background. Yeah, I got some comments last time saying my color scheme was a bit too bright for the eyes, so I wanted to kind of see if I could find a different light theme that was still light but like not super harsh. Check fit. So what is this doing? It's going through. It's literally starting at physical memory 0 and checking that kern base is, it's checking that kern base, the kern base region maps to physical memory, which is actually not new. So what that's talking about is we have this kern base region all the way at the top. And that's kind of where the kernel is like compiled to operate. It's kind of in like high memory, but it is just a 4 megabyte region that is mapped to where the kernel gets placed in physical memory. And this is just a very fundamental basic thing that we've already set up actually. So I actually kind of think this should pass too, and I will try that. Does this pass? No, it failed. Okay. Game development. No, never done any game development. Seems cool though. I think game programmers are like some of the best programmers out there. But yeah, no. So what happened? So obviously I'm missing. Oh, okay. So I must be misunderstanding something because I assumed that this was already set up. But it's not. Oh, Oh wait, okay. So I misunderstood something. So it's testing. Okay, so this expression computes the entirety of physical memory, and we bump along literally all of physical memory and make sure that we have a mapping, which is not which actually is different from what we currently have. Currently, we only have 4 megabytes mapped, but now this is saying we actually want literally all of physical memory mapped. It's an operating system. It's a basic learning operating system from like this MIT class that I'm following. So anybody can follow along with me. I think a couple people are actually following along in the Discord at their own pace with it too. But it's not it's not really my OS. It's just like this learning thing, and I'm just kind of doing the exercises. But eventually I will write my own OS. Once I learn how to do it, I will start from scratch and write my own OS. So, right. So maybe let's read the comment. It's interesting that it's first checking this physical memory stack thing, which is this check over here. Then it checks that all of physical memory is mapped, but that check comes first. Interesting. I don't know which is easier. Awesome, appreciate this. Yeah, I do this every week. I also tweet about it sometimes. I mean, I tweet about it every week, but I tweet what I learn or like the takeaways of the session usually too. I think this one will be easier. Map all of physical memory at current base. The VA range current base to the top of 32 bits should map to 0 to 30th to the minus current base. Okay, that makes sense. We might not have that much physical memory, but set up the mapping anyway. Okay. I think that's going to be exactly the same. Boot. It's actually super handy to know, to like remember that we have this function available, which just maps large swaths of address space, current base, and it's going to be size. I'll do that later, and it's going to map at 0. Is there a better way I can do that? I'll do a cast to try to communicate what I mean. And PTE writable. But actually, I just noticed an error. Okay, I just noticed an error, and it's in the permissions. The error is not caught by the test because it doesn't check this at, oh, maybe it checks it later. Let's see. The issue is that actually this range should be readable by user space, but I didn't actually allow that in my permissions. By default, user space doesn't have access to mappings, and we need to specify a permission. But I don't actually see any test for this. So actually, yeah, that would have been like that is a bug though, and it's just not tested. And we can't test it because, well, maybe we can actually. Never mind. Yeah, it's totally possible to test that by looking at the page table entries. There just isn't a test. All right, 20 seconds. Yeah, just for a little bit of a refresher on that one. So it goes back to the page table, like specification. And specifically, it's this user supervisor bit. And if the bit is 0, user mode is not allowed. And by default, all of these bits are zeroed out in our implementation. And then we selectively change bits to 1 to kind of make the permissions more lenient. For example, by default, like pages are read only and kernel only. and then we selectively relax them by like adding 1. So if we want to make it readable, we add a 1. If we want to make it user mode accessible, we add a 1. And so I was not doing that. And maybe I'll take the opportunity to try to do some test-driven development. How would I, so I could try to add a quote-unquote unit test for this or something like that. So because it's missing. And what would the unit test do? I would need to look up the page table entry, page dir walk, which I forget how it works. Kern page dir, given the virtual address, which is what? It's u pages plus I, right? And false. I don't want to create anything. PTT, PTP, const, and I'm going to assert that this has a value, and I'm going to assert what? It's going to be like PTEP and PTE U. I'm going to assert that that bit is set. And I'm going to assert that it's not writable in this area. That's not. I am not totally sure if I did this right, but I think it should be close. Accessible? And this test should fail because I have not fixed the bug yet. Let's try. Doesn't compile. Oh, okay. Cast. So this thing takes a pointer. By the way, I just found out about this awesome Vim plugin called Vim Sneak, which is how I moved around so fast just there. Like with Vim Sneak, you press S and then 2 characters and it jumps. It's kind of like a fast search. So let's say my cursor's up here and I want to quickly jump to this U pages thing. I do S, UP, and now I'm there. I press semicolon and I'm there at this one super quickly. And I can like go back around and I can like jump back to where I was. So it's super awesome. Big fan of Vim Sneak. So let's try this again. Right, and it failed. Assertion failed, PTP, and user space, which is good. So now we have our, now I'm doing my complete good practices for kernel test-driven development. Now I go and fix my code and make it PTEU. And now hopefully the test is not going to fail. But then this one failed. What? Oh, wait a sec. Actually, it did. It failed because I'm literally adding the writable bit, which I think is wrong. I think, yeah, it's failing because I have a writable bit, and it's literally saying, don't make it writable. I was kind of confused by this thing, but I still truly don't know what's going on with that, because none of this test function seems to, I don't know, mention it. So I don't know what to think. So actually though, so that's funny, in the course of actually doing the test-driven development, I actually found a second bug in my code. Because if I had just gone ahead and fixed that first bug, I wouldn't have noticed that it was actually incorrect to have the PTW there. But in the process of writing the test, I actually clarified a couple of my own assumptions and I guess invariants I want to check, and accidentally discovered that one of them was being violated. So now let's try one more time. And now we're at 870, which I think is where we want to be. So yeah, now we're back at the original one, which is cool. So I kind of want to just do a quick commit while I'm here, just to kind of check in, do a little progress checkpoint. Yeah. So it's gonna be a whip. This might get merged in later, but whip map u pages and extend test. Send tests. The tests were not. The tests did not have any permissions checks. Commit. Boom. Yeah, and also, if you're new here, you might not know that I'm I'm pretty into Git and stuff like that, and I'm like really into clean commits, and like I didn't just fully commit everything in here. I like to selectively stage parts of the working tree and then only commit what's actually necessary. And so and here the commit is pretty minimal. It's only exactly what and yeah, it's just what's relevant to this chunk of code. Hey, Dimensio? Kind of don't know how to pronounce that. Great content. Thank you, appreciate that. I am at a very early stage of this. Yeah, I would say very, very, very early stages. That like the kernel doesn't have any features. The kernel doesn't even boot. I haven't even reached, like I'm still setting up like the core virtual memory to get the kernel even like running. So super early. Okay, let's I want to do this second one. This sounds easier. And I kind of already started before I saw that bug. So okay, map all of physical memory at this place with kernel read and writable, which is what we're doing. And all we need is size. And what is size? Size is so it's n pages times page size. What is wrong? Something wrong? Yeah, I think my like the C plugin or something like that is a little bit slow. So theoretically, that should actually do it. I'm mapping. So first of all, n pages is the number of pages, like 4K pages of physical memory that we have. And each page size is 4K. So if we multiply those two numbers together, we get the full amount, like the full size of physical memory, which in practice is 128 megabytes. And we're saying that we want to map, starting from kern base, that big size, that whole region, the region that is described by kern base plus this size, should get mapped to physical address 0, which I feel a little bit weird about just like passing in like a 0 like that, but I tried to cast it to physicadder_t just to communicate that a little bit better to the reader of this code. Because it's usually kind of odd, because that is like a pointer, and it's very rare Maybe I'll add the 0x just to be a little bit more clear. I don't know. That's kind of like I don't love that either. Anyway, now let's see. So first, comment this out real quick and observe the test failing. And it fails at 870, which is like in this code. So now step 2, add the production code, and let's see, do we hit the panic? We should hit the panic. We hit the panic. So done. So that means we successfully did this part, and we can move the panic down even more. So now it's time to do this other part, which is the kernel stack. And I just need a moment to like read this. Quick check in on the stream quality, just make sure it's like still okay. But okay, seems like it is streaming still. Okay, use the physical memory that boot stack refers to as the kernel stack. The kernel stack grows down from virtual address k stack top. We consider the entire range from k stack top minus pt. What is pt? Minus pt size up to k stack top to be the kernel stack. Break this into 2 pieces. It's like top area with k stack size. Oh, okay. Okay, the actual kernel stack and then a guard page. Pretty typical thing. So yeah, I think they illustrated pretty well. So we have our stack, which is immediately below kern base, and immediately beneath the kernel stack is a page of memory that is intentionally left unmapped, because it would be, if we didn't do that, if we actually mapped some other like data there, it might be possible that the kernel has a stack overflow in case we call too many functions. And then if we had other data right below there, which was read-writable, we would start to silently corrupt all that data below the kernel stack. And so as an alternative, we can decide to intentionally leave one page always unmapped, so that if that happens, we will get like a page fault, like an assertion, or I mean specifically it will be a page fault. And as like a developer, we can like notice this. And so the trade-offs here are that, okay, by doing this solution, we get some safety, but we trade off we trade off 4 kilobytes of virtual memory space, which we can't use. Because in the other solution, or in the other world, we can have less safety, but we can actually use that region. But the trade-off is well worth it. So we'll have the invalid memory page, guard page. And that's pretty much, all right, this is like kind of fun. Now that I'm like kind of understanding how to do this, and I've written all like the hard code in the last couple weeks, I just get to call these functions, which is kind of nice. So I need to map the stack. And I'm mapping, what is PT size though? Kind of don't know what that PT size thing is. Page table size? What? Bytes? That is so random. Page table size is the size of a page size times the number of page table entries. which should be 4 megabytes. So, okay, so it's saying stack top minus 4 megabytes. That is so random that they use this. It's like, what we're doing right now is completely, I mean, it's not really that relevant to the stack. The actual motivation there is that apparently we want the stack to be, we want to have a single page directory entry that is fully is fully committed to the stack, basically. Like a page directory entry, it can map a 4 megabyte region, and we want everything within that region to be like stack. But it's just a little bit confusing that they use PT size there. But I can kind of see it. So we have a 4 megabyte stack starting from this like location. So, and it needs to map to the boot stack region. And let's refresh on the boot stack. I'm gonna pop over to this other one just so we can read a bit more clearly. So I think boot stack, searching for boot stack. Meminit, no, I think it was in the caller of meminit, which is init. We set, maybe not. Maybe it's in the caller of i386 init. Shit. Oops. Init. How do I? Sorry. Oh. I was just trying to get the references to this thing. There we go. But it's, wait a sec, okay, I'm kind of getting confused then. It's called from assembly. Oh, okay, yeah, boot stack top. That's right. We set up the stack before C code, which makes sense because in order to be running C code, you need to have a stack. So to find where the stack is set up, we need to go before C code, which is in our assembly entry.s. And it's actually quite simple. It is really just like a bunch of space that is reserved in the binary. And if I remember correctly, it's not even in the BSS section of the kernel binary, which means that it's actually taking up a ton of space in our kernel binary for the stack, which it shouldn't. And like, it's just not necessary. We should be able to have this region where the kernel stack, instead of being allocated in the .data section, which actually occupies space in the binary, which you usually use for actual like constants and string data and stuff. Here we just have this region that we want to be available at runtime, but it's just all zeros. Like, we don't care what it is, and that should go in the BSS, which would save on the binary size. And it's 8 pages, 16K of stack size. All right, 20-second break. Okay, so that was just a bit of a refresher on how the stack works. And now what's it saying? It's saying we should we should map this like large region I'm actually a little bit confused because this region is 4 megabytes. It's like really big. But the boot stack is not, it's like much smaller than that. It's only 16K. So I need to think about actually what to do here. I don't immediately understand it. Okay, but break it into 2 pieces. K stack top minus K stack size, which is the current boot stack. Interesting. Okay, that's a bit easier. I will give this a try. So the next argument is what? The VA, which is K stack top minus K stack size. I think it's just literally what it says there. Excuse me. K stack size. Oh. Okay. I'm just kind of drafting it out. We'll see if it's correct. So now we want boot stack, and it should be PT writable. So boot stack corresponds to the bottom of the stack. Pretty sure about that. Let's check over here. Boot stack, yeah. We have the boot stack symbol, and then after that we inject like a bunch of space and then get the top, and then we have both the start and the top. So this is the virtual address. It's K stack top minus stack size, and we're mapping the region that is described by that pointer with stack size, which is our current, which is where we want the stack to be. We're mapping this to this boot stack region, which we know is K stack size, and we're making it writable. I think that's correct. But it's also saying we need something else. So now we need the guard page. So I understand the concept of a guard page. I also realize my lamp is not on for YouTube lighting. Put that on. I understand the concept of a guard page, but I've never implemented one before, so I need to think a little bit about what that means. Because it's saying, okay, there's this region. Wait a sec. Oh wait, okay, I misunderstood something. This entire region, K stack top minus 4 megabytes up to K stack top. It's a 4 megabyte region that is collectively referred to as the stack. But in actuality, the actual stack data is only the top 16K of actually this 4 megabyte region. And the rest of it, K stack top minus PT size minus 4 megabytes up to K stack top minus K stack size, which is like, 3.9 megabytes, or like just the vast majority of that region is not backed. That was a bit different from my initial misunderstanding of it. Okay, it's not backed, so if the kernel overflows, it's not going to fault. But what's funny is that it's not just one guard page. It's like 1,000 guard pages. All do you really need that much guard page? So it's not clear to me why we have so much guard page. But okay, so that is clear to me now. But I still don't really know what to do, because I know how to map something and make something point somewhere, but I want to explicitly like not map on something. Which, like, does that take any action? I think like by default nothing is mapped. And so if you want to make sure, if you want to have something be not mapped, I think you don't need to take any actions, as far as I know. I'm just like thinking about whether I could like map it, but then make sure it has no permissions, so you can't read or write to it. But that doesn't make sense because you cannot actually remove read permissions from like a page. We only have 1 bit on x86 for this. Pages are either read or read and write. There's no non-readable memory if it's mapped. So I don't know how I would like map something, but then like have it not. Yeah, so I am a bit confused. I'm not sure if I need to even do anything to satisfy this like second part of it. So let's see what the test does. Oops. Go back. Okay. So check the kernel stack, and it goes through all of this region page by page and checks that the kernel stack is mapped. And then, so I think we should actually pass this. So I'll just go ahead and move this here. We should pass that one right now. Doesn't compile. Okay. What does not compile? Hello? Make the integer from pointer without cast. So boot stack. Okay. So what is it expecting here? A pointer? No, it's like a. It makes integer from pointer. And so boot stack is a pointer. And just adder t. That will do it. So now it should compile. And now we'll run it. And 876. Okay, so I'm actually okay, so I have an issue. Hey Zinx or Zynix, any winning resources to make sure you understand this all. Yeah, this question comes up a lot. If you go to my blog at offlinemark.com, I have a blog post with some resources. Just go to like the archive section and you can search for resources. Yeah. But you're asking if I understand, to make sure I understand this all. I mean, I'm just, yeah, I think I don't need so many resources. I think I know a lot of this already, but I've just never written the code before. So I'm just going through the MIT class specifically. That's my resource, I guess. So this assertion is failing. 876, right? Assertion failed. I'm actually kind of surprised because I thought I did this. So that means I have like some mistake. Just to make sure it's really failing at 876. Okay, what do I do? I don't. So the test is checking for like bumping along at every page interval in the stack size region, which is 8K. I think I was saying 16K before. It's 8K. We then compute, we take the stack top minus stack size plus the offset. That's a virtual address. We convert that to the physical address that it's currently mapping to. And we make sure that it's boot address plus I. And I feel like that's what's happening, so I'm a bit confused. Is this code even running? just quick panic just to make sure. 1, 2, 3. Okay, it definitely is running. So the permissions is not relevant here. It's not checking permissions. It's just purely checking. This is a void function, so there's no like return code I might check. Okay, what? I guess now I kind of want to see specifically which yeah, how, like, sorry, oops. Okay, what do I need to do to get some more info here? I mean, I guess I can just start printing stuff out. X? I always forget this. 8x or something like that. I actually don't know if that will be helpful. I'm just going to print this. 0. That's interesting. It did not even. The first one doesn't even work. I'm gonna move this over here. Okay. No, I'll move it over here. Okay, so I can get some more space. Right. So it's saying. I wonder. There's not actually that many places for me to be making a mistake here. It's just in these. Oh, I wonder if it's. I wonder if it's some like C thing. Unit pointer VA. And what are these? These are just numbers. Which should fit into a unit pointer VA. Assertion failed. Kernel panic. So, and this code is executing. What? I kind of don't know what's going on. What if I comment this out? Just curious. It should still fail, right? Okay, A71. Okay, now it fails at this other one, so I kind of need to have this one. But if I comment this out, just for the moment, just to make sure, 878. So it's, okay, yeah. So it's not related to this thing. I can leave this in. And on the actual, this first try of the loop, it failed to resolve. And how do I get, like, please tell me what actually failed. So I want to know F. So I want to know do I want to know? I want to know, so this is the resolved PA. And I probably want like a big hex number. And then this is going to be, no, wait. Expected PA. Oh wait, no. This is the expected PA. The PA. And this is the actual PA. And these are, I guess, different numbers. So yeah, I'm just trying to get some more information about this. So, because there's a lot of stuff going on within this single assertion. Ah, okay, so now we get a bit more info. Oh, I see. I totally get it. Actual PA is F blah blah blah. Expected PA is blah 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 blah. Is the same thing without the F, and I know exactly why. It's because I made the error of I forgot that any, like, almost all like symbols and pointers and like everything in the kernel binary is going to be a kernel virtual address, and that parameter needs to be a physical address. And this is the way you do the conversion. So bootstack is a kernel virtual address. It's like a variable that has a kernel virtual address inside of it. So now I'm going to remove all of these things and run it. And it succeeds, 884. So now we're here, so good, so good. Okay, glad that wasn't too painful. I'm gonna get rid of all this stuff. And get rid of this straight line. So now I'm passing the basic version of the test. Now what's next? Assert check. So virtual address is. Oh, what is going on there? K stack top minus PT size. Okay, so minus PT size, so there's like 4 megabyte region. It's all the way at the bottom of this from there. And also, hey Jan, thanks for tuning in. Actually, Jan, I've since changed tax a little bit. I am not using x86 anymore. I'm using this thing called JOS, J-O-S, which is way more minimal. So I'm still following MIT stuff, but it's it's all part of the same class, but this is the second half of the class where you actually do your own OS. So in the first half of the class, you read x86 and learn stuff, and in the second half, you like clone this JOS thing, which has almost nothing in it. Yeah, I'm finding that it's a much better fit for me because there's like almost nothing here. So this is kind of funny, actually. This is like kind of weird. It's saying, if I take this, okay, 20-second break. Be right back. All right. Yeah, I stopped doing x86 around episode 13 and have been doing this JOS thing ever since. Okay. So, but this is very interesting though. It's asserting that k stack top minus pt size, which is like 4 megabytes. If you take that virtual address and resolve it to a physical address, it should be equal to like all the like, oh, I see, it should be equal to, I mean that like tilde 0 is like invert all the bits, and it is very non-obvious what this means unless you remember that that's the error return code of this check function. It tries to return a -1 basically, but the function must return an unsigned 32-bit int. And so it just like it's like does that by pure force and returns an inverted like 0 as its way to return an error code, which is like very funny. So basically what this is actually saying is that this function should return an error. Yeah, there should ideally be like some kind of macro there or something like that, I think, or at least a variable name to help communicate that. Yeah. So then the real question is, I think I should, like, I've not taken any action to map that page. So by default, the page lookup should fail, which means that check function should return the tilde 0 -1 thing. So I actually think we should, yeah, 877 panicking. Yeah. So we've totally passed all those, which is sweet. Okay, so no action necessary to map the guard page? Question mark, 'cause I'm like still like I'm mostly sure that you don't need to do anything to map a guard page. The mere absence of mapping something is sufficient to have the guard page be there, and the test seems to suggest that also. So moving on, and now I have officially done all of the commented like exercises I need to do, which means maybe I will just take out this panic and see if this PD permissions thing just magically passes, because I did all the rest of the code right. And nope, I did it wrong. Okay. 892, what happened? So something is not writable that should be, which is interesting. And specifically what? It's going through every single page directory, and okay, by default, okay, there are some specific exceptions where it should be present. Okay, there's some specific ranges where it should be present. And so if we're in the U pages range, it should be present, and that's it not writable. Oh, actually, wait a second. That's kind of the test I tried to add a little bit earlier. But I was checking the page table entries actually, not the and this test is checking the page directory entries, which is kind of different. So yeah. So it was actually worth doing my test-driven development and adding this test. And it wasn't a waste. But so specific ranges, so the U pages range, the K stack top -1 range, interesting. So yeah, oh, I see. And that's because, so okay, interesting. So this decision that they made to like spend an entire page directory on the stack, where the majority of it is unmapped, except for the tiniest little like 8K chunk at the top kind of seems to be just so it can make this test easier to write, it seems. It's not because if we decide to spend an entire like 4 megabyte page directory on doing that, we can just say for any page that maps that like corresponds to this page directory. How should I say that? So kstack.-1. Maybe I kind of misunderstood something. It's just saying, okay, let's just make sure that the stack page directory is present. There should actually be some more stuff, like it should actually be writable in this case, but like maybe I could even improve this a little bit. So upages is read only, but kstack should actually be writable. But I'm not totally sure if that is reflected in the page directory entry or if it's just in the PTE. I do not immediately know. I kind of also don't want to find out. It's not that important, I think. And I don't know what this UVPT thing is, but we haven't had to deal with it so far, I think. So, happy? What's UVPT? Well, okay. Even though nothing here said to do anything about that, right? I didn't see the word UVPT anywhere here. So I didn't do anything, but this is going to fail because it's going to assert that it is present. And I didn't do anything to make that the case. So I should expect a failure immediately just because of that. I think that should be fine. That should be fine. And then also by default, in general, it's saying for everything else, the page directory entry should be empty. However, for everything above the current base region, it should be writable. Yeah. I think we totally satisfy this with what we're doing here. We satisfy the stack thing with what we're doing here. We satisfy the upages thing with what we're doing here. The only thing is the UVPT, which I don't know what it is, and we're going to fail the assertion because of it. This is my prediction. Let's check this out. 892. Actually, so that was kind of counter to my expectations. It's saying we're failing this write bit. It's saying something it should be writable, which is not writable. Oh, spooky. But okay, but this is in the page directory entry. Interesting. I think that means I actually have a bug in some of those more core like functions then. Wow, okay. So what's going on? My test is failing because, and this is actually quite interesting, it didn't fail this thing. So I had two expectations. Expectation number one was that this thing would fail. This assertion that the UVPT was present, that should fail because I didn't do anything related to UVPT at all. Which means it's not present, which means this should fail. this did not seem to fail just now. So that's unexpected to me right now. Expectation number 2 was that this should pass because it's checking that all these pages are present and writable. And I was pretty sure that I did that because of this line 230, in which case, like where I map this large region from current base with the PTEW permission, which is writable. And so like things are kind of counter to my expectations in 2 ways. And I will start by looking at the one that's actually failing right now. Which is interesting. So here's my guess. My guess is that the code inside bootmap region has a bug. Bootmap region is like doing a bunch of page table stuff, and it's like setting bits in page table entries to point things at physical pages. It's setting like permissions bits and stuff like this. And here's my guess is that this function has a bug where it doesn't actually modify the page directory entry properly, which I think is totally true. Like I think I have no memory of writing code that modifies the page directory entry. I mean, the function's very short, and we can just immediately see that the only place where we are modifying like these like entries, like page table entries or page directory entries, is right here. And that explains why the page directory entry is not being updated, which is interesting because I actively remember updating them somewhere else. So specifically here. So this is in a bit of a separate part of the code called page insert, which is doing kind of similar things. And I think I actually need to copy paste this code. It would be kind of nice if I didn't need to do this. And now I'm actually just wondering if I should refactor this function to use page insert, because it already takes care of this thing. Let me see, maybe that makes sense. What would that look like? Basically, I need to replace the pagedir walk. But actually I don't know, because this thing manipulates ref counts. And that was specifically forbidden in the comment here. So that was specifically forbidden, so I think I can't reuse that. Yeah. Hey Ram, I'm writing in C right now. Okay. Yeah, so let me give this my best shot. So the general idea is we look up for every yeah. I'm going to copy and paste something like this just to have it available for reference. It's not totally right, but it's like kind of close, I think. I'll just comment it out for now. So we need to get the page directory entry. I will answer the questions in 1 sec after I try to fix my code. So first off, we need to get the page directory entry. And we do this. And maybe I'll even put this after, just at the end. So now we are like loosening. Yeah, we're loosening permissions, and we are like more specific, to be more correct, I think we are like propagating permissions changes correctly to the PD. I think that should be enough to make the test pass. So now it's a different error. So Rom, can I teach Python on live stream? Probably not right now, unfortunately. For a couple reasons. Like right now, I am pretty much only interested in doing C programming and operating systems programming. That's all I have time for. And I also, it's kind of been a while since I've written Python actually. And I probably wouldn't be the best teacher at the moment. Yeah. Coding with a kernel with Python would be super hardcore, and I don't even know if it's possible. Yeah. The dev Zig programming language. I know almost nothing about Zig. So I'm not super well equipped to answer that. I don't have a lot of opinions, other than the fact that I think it's awesome that people are innovating in the space, and I know a bunch of people use it with a lot of success actually. So I'm curious about it, but it's not like in my order of languages to learn. I would probably try to learn Rust first and then Zig. I run this in QEMU, however you pronounce it. Yeah. Opinions on Java. I got no opinions on Java. I haven't really written Java like too much ever. I'm sure some people like it for good reasons. Let's get back to coding. Okay. I'm definitely not perfect with C. I'm definitely not a perfect C programmer. I know C well enough to do this work, but I wouldn't say I'm like an expert. I'm like competent, I guess. Maybe. Competent enough to do this. So the error is what? 897. So something wasn't even present. Wow. But what the hell? Why? Okay, I think I could use a printf here. I'm just gonna do a D. Nice and simple. So I want to just rewind 1 second. So I'm going to undo this change and observe the original failure, which was at 960. Yeah, I'm just following some coursework from this MIT class. Yeah, it's the 2018 version of the MIT operating systems class. So 960 failed with not being writable, and apparently that was actually the very first page directory entry, because there's only one print with a number. So now I'll add the fix and rerun the code. And a bunch of stuff happens. It gets a lot further, and then it fails. A bunch later. Like a lot later. I mean, not that much, but it's like, okay. And something wasn't present, which is very unusual. would something not be present? So again, we're looking here, bootmap region. Just curious, is it writable? Or is it neither? Was it 992? I think it was neither. 992. Um, 898. Sorry guys, I gotta focus on the code right now. Oh, and also time for a 20-second break. Be right back. Okay, something. Oh, wait a sec. I think I know the issue actually. Right, it's this thing. We should be mapping. Basically, we should be mapping everything from kern base to the top of memory, and that is a 256 megabyte region. And that's not what I did. I actually misread it, and I only mapped the physical memory that we have available, which is only 128 megabytes of space. So I kind of wonder what I need to do. I think, is it as simple as what's actually the best way to do that? It's kern base. Like, I mean, just conceptually, I want to do 2 to the 32 minus kern base. Like, you cannot actually do this in C. This is not exponentiation in C. And so maybe I'll do. I mean, I can just type out the constant. It's right. Okay. I mean, I think I'm actually being kind of stupid right now. There's definitely a better way to do this, but I think the test should pass. Yeah, the test passes now. So yeah. But that's kind of like, yeah, I could use a shift. I could be like 1 shifted all the way down to get 4 gigabytes. Maybe that's actually the best way. So, const. What is even the type of this thing? Like, I was kind of getting tripped up because like, wait, okay, kind of brain fart right now. Like, I'm on a 32-bit system. So can I even represent numbers above that? It's probably a dumb question. Like an int, like especially not with an int, with an unsigned int, I get 32 bits of numbers. But this number is bigger than int max, than unsigned int max. So that's kind of why I was getting a bit tripped up by that. Also, what's this squiggly line about? I'm actually super curious. Yeah. Okay, I take back what I said about me being competent in C. I'm like not competent in C. Like truly, how do you represent that number? Like if I have like uint 32t num, I kind of want to get a compiler warning about that like my number is too big to represent. Yeah, like that's what I would expect to happen. Like I'm trying to have a number that's like way too big for a 32-bit uint. So do I have 64? I guess, do I have 64-bit uints? So now this, oops, shit. So now this should compile. And maybe that's what actually happens here. It's using, but also like what the, how do, is that a dumb question? How do 64-bit uints work on a 32-bit, x86 32-bit? Does anyone know? Like, does anyone know? I feel like that should be kind of a basic question. But I don't know. Like, I never work on like 32-bit systems. So usually this is just not an issue because the base platform supports 64 bits, but so John, you're saying just take hex FFFFFF all the way. But that is slightly like not correct because, I mean, I think it might work. I think it probably will work, but this argument is really the size of the mapping. And if I do FFFFFFF, that will be one too small for what I actually want. Fuck, how does this even work? But that's not really relevant right now. I am just going to be content. I mean, there's definitely a better way to do this. Like, I mean, at the very least, I could have a variable. But I mean, that exactly, like, what's the type of that? That was the original question. And virtual memory full size. Virtual memory full size. And that is at least a little bit more clear. And maybe even to be like a really good programmer, I could do to the 32, right? Does this work? Oh no, I think I got it. Shit, did I get that wrong? Okay. Actually, though, wait, there's 32 bits, right? And I want to put a 1. What was that error? Width of to size T. Interesting. Long, unsigned, signed, and unsigned. Oh, and okay, I think something like that, maybe? Okay, yeah. There we go. Okay, so apparently you can't just use 1 because that's like automatically interpreted as a size T or unsigned int. But you know, to be honest, I'm just gonna leave it kind of like this and not. I think that's just a bit clearer as to what's happening. Even though I kind of don't get it. So, and with that said, things are working. Now we're at pmap.c 241, and and that passes. Which means I got it to work. Now I've moved just a couple steps forward with this, and now we have some initial memory mappings that are set up correctly. And you know what? I think that's a good point to stop the stream. Yeah, thanks a lot for joining. I'll just take a second to plug myself. If you liked my stream, yeah, you know, comment, like, subscribe, all that stuff. I have a Discord server, which I'll post right now, the link to. If you feel like chatting some more, I'm here every week. And yeah, with that, yeah, thanks a lot for joining, and I'll see you next week. Peace.